Hi, so I hope everything's working. I'm just going to do a quick video to go through some of these examples, primarily for the benefit of AP students taking the statistics module at 4 Ways High School, but perhaps this would be helpful for all sorts of people who might stumble across this video. We're just working through some examples of a standard advanced mathematics course of statistics at a high school level / first year university level statistics. We have some questions in front of us, and we're just going to go through them. These were given as homework. At the bottom I have all the formulas that would be provided in an examination such as this, and it's very formula based. All of this is very formula based, so if you know what all of these formulas do, you should have no problem. So yeah, let's solve these issues. This might be a bit untidy. I'm going to do it all in Paint, but I'll just solve the equations one by one over here, and since it's in a video format recorded for posterity, I don't think I need to keep everything here. I'll erase it as I go. Okay, question 1.1. A collection of antique toys containing 6 train sets, 5 model cars, and 3 vintage toys are displayed at an auction. 3 of these items are sold. Find the probability that all 3 items sold are of the same type. I must say, I haven't solved all of these yet myself, so I might actually have to think a little bit. But that should show you my thinking, so it might be helpful. This is an example of, well, let me not say it yet. The most important thing in statistics, as we all know, is working out which formula to use. So when you see this type of thing, you should immediately ask yourself, which formula is this? In other words, what type of distribution are we dealing with? What type of equation are you dealing with? You are selecting objects where there is more than just 2 possible outcomes. Repetitions are not allowed, because when you take from the 5 model cars or the 6 train sets, for example, let's say you take from the 6 train sets, well, now there are 5 train sets, and if you take again, there are 4, and again 3, 2, 1, suddenly there are no more train sets. So you cannot take any more train sets. The repetition is not allowed. However, the order doesn't matter. If you take a train set and then a model car and then a train set, you end up with 2 train sets and a model car. It's the same as if you take a train set and then a train set and then a model car. So the order doesn't matter. That's all the criteria satisfied for the hypergeometric distribution. And let me say, everything I just did is the most difficult part of statistics. Figuring out which formula to use, that's the hard part. Okay, but you got to practice that in any case. Here we go. It's the hypergeometric distribution, which is this formula over here. That's the formula we're going to be dealing with. Perhaps I should just grab it. This one, the hypergeometric distribution, does not necessarily only have to have 2 categories. The way you see the formula one here makes it look like there are only 2 categories, but there does not have to be only 2 categories. There can be 3 or 4 or whatever the case may be, and you'll see in a second how that works. Essentially, the denominator stays the same and the numerator just keeps decreasing until you're finished with all your categories. In other words, you start with how many you want of one thing, move on to the next until you finish all your categories. Okay, so we start with this. Here's the formula. Now, the formula we use isn't going to look exactly like this, because this is reserved for only 2 categories, whereas we have 3. So let's just keep track of them. It contains 6 train sets, 5 model cars. I'm just writing this here so I can remember, and 3 vintage toys. The question is, 3 of these items are to be sold. That means that we are going to pick 3 of these things. So the total number of objects we choose will be 3. By the way, immediately you know that means that little n equals 3, because little n is the number of objects to be chosen. Big N is always the absolute total, which would be 6 plus 5 is 11, plus 3 is 14, so we know that. And what else is there? Find the probability that all 3 items are of the same type. So essentially what we have to ask ourselves is, how could this occur? How could you have all 3 items of the same type? You can either have all 3 items are train sets, all 3 items are model cars, or all 3 items are vintage toys. So this is just going to be a sum of something that looks like this. So we'll see, what is it going to be? Find the probability that all 3 items are of the same type. Well, let's check. We think we have 3 possibilities. All 3 are train sets, all 3 are model cars, and all 3 are vintage toys. If we want to add those probabilities, we have to ask ourselves, are they mutually exclusive? And if so, then we can add them. Remember, that's the idea. If you want to multiply probabilities, you have to check whether they are independent. Not check, but that's the question you have to ask yourself. Are they independent? Then you can multiply probabilities. If you want to add probabilities, you have to check whether they are mutually exclusive. So, can these 3 things occur at the same time? Can it simultaneously be true that all 3 choices are model cars, or all 3 choices are vintage toys, or all 3 choices are train sets? No, that cannot simultaneously be true. It must be one or the other, which means they are mutually exclusive. So we can add the probabilities. That's the idea. So what are we going to do? We're going to take the probability that all 3 are train sets, or, and because it's mutually exclusive, that or turns into a plus, or the probability that all 3 are model cars, or, and this also turns into a plus because of mutual exclusivity, the probability that all 3 are vintage toys. Okay, that's the idea. Mutual exclusivity. Now, as I consider this question, I realize each of these is actually going to only involve 2 categories of the hypergeometric distribution. But I'll quickly give you an example of if there were ever 2. More than 2, excuse me, and that's not that bad. Okay, so what's this? The chance that all 3 are train sets. Well, we've got to keep these numbers in mind. So let's go. What's the probability that all 3 are train sets? Well, we need some brackets on the top, and we need some brackets on the bottom. Now, the brackets on the bottom will never change, because the total number of choices you are making is always 3, and the total from which you are choosing is always 14. That'll never change. So let's copy that and put it there and put it there. Okay. Now the plus comes from the fact that it's mutually exclusive, and we have an or, so we plus and we plus. So those 3 will always be the same denominators. Now the numerators, we have to think differently. Recall that P means how many are there of the object you want, and then R is how many of them you expect to get. Then N minus P is whatever's left over, and N minus R is whatever. So let's check. How many trains are there in total? The P up here is the total number of things that you want, and the R is the total number that you desire to choose from them. So you want trains. There are 6 of them. How many would you like? You'd like 3. You want all 3 to be trains. What's left over? What's left over is 14 objects minus the 6. So that's 8 things left over. How many choices would you like to not be trains? 0. By the way, this evaluates to 1, so you wouldn't actually even have to calculate this, but the idea is that from 14 things you're choosing 3, 6 of them, perhaps I should highlight them. From 14 things you are choosing 3. From 6 of them, 3 must be of that type, which are train sets, where the total is 6. From the remaining 8, you don't want any. It should be easy to fill in the rest from here, I think. Let me scroll over. I don't think the recording captured all of that. I was a little bit off. Okay, now, what about here? Next up, all 3 are cars. So from 5, you want 3. And from the remaining 9, you want none. You do not want any to be of the remaining 9. Lastly, we've got vintage toys. There are 3 of them, and you want all 3 to be chosen. You always want to choose 3 from that type, because you want all of them to be of the same type. If you see a faster way of doing this, because it does look like a lot of these terms simplify, if you see a faster way of doing this, feel free to implement it. However, in a test situation, it's never a good idea to try and be smart. Rather just use the formula, stick to what you know, and chug your way through. So from 3, you want 3. All 3 should be that. There only are 3. If there were fewer than 3, by the way, this probability would be 0. If there were only 2 and you wanted all 3 to be of a certain type, then the probability of all 3 being that type would be 0. You can't get 3 if there are only 2. We continue with how many are left? 11. And you want none to be from 11. Okay, I don't think I'm going to evaluate these numbers. You can all do this. I mean, this evaluates to 6 combination 3 over 14 combination 3. And you can just put that into your calculator quite easily. This evaluates into 5 combination 3 over 14 combination 3. This last one is easy to write down because 3 combination 3 is just 1, 11 combination 0 is just 1, so this comes out to 1 over 14, combination 3. And I think in the interest of time, I'm not going to actually put this into an evaluation tool since it's so easy. There's nothing to really check here. 14 combination 3 is too big for me to do in my head, so you put this in your calculator, you get the answer. Cool, you're done. That's the answer to that question. Perhaps I should just mention, what would you do if there was more than one category quickly? Just for example, I'll quickly mention here, what if you said, just this is a very, very contrived example, 3 green marbles, 5 blue marbles, and 7 yellow marbles. Okay, let's imagine that those are your choices. Those are the objects from which you want to choose. And the question would be, what is the probability that if from this total of, how many is that, 15 marbles, you take 7. So from the total of 15, which are composed of these 3 colors, you're going to take 7 at random. You put all 15 together, so the 3 green, the 5 blue, and the 7 yellow, you put them all together into a big jumble, mix them up, perhaps 15 marbles, you take 7 out randomly. You take 7. In that 7, and this is always how hypergeometric probabilities work, it's always in the choice you make, which in this case is a 7, how many have a certain property. So what is take 7, what is the probability that if you take 7, I've already written that, 2 will be green, 2 will be blue, and 3 will be, it has to be 3, right, because you've taken 2 and 2, which is 4, but you're taking 7, so there must be 3 left. 3 will be yellow. Now we have very specific demands, and hopefully you can see there are actually 3 different categories here. This is still very easy using the same formula. Start with the denominator always, makes your life easy. What's the total? 15. How many are you taking? 7. It's always like that. And now you just write all of the factors on top, going down for each category. So you start with, the order doesn't matter, of course, multiplication is commutative. So let's go. Put the totals up here. We've got 3. You can even write the letters on top if it helps. You put a G, these are the green marbles. Put a B, these are the blue marbles. Put a Y, these are the yellow marbles. How many green do you have? 3. How many blue do you have? 5. How many yellow do you have? 7. And now you simply write what you want. Hopefully you're seeing the pattern. The denominator is always the same. It's always easy. It's always the absolute total in combination with the total that you are selecting. 7 are being chosen from the 50. And the numerators are just the categories. The total of each category in combination with how many you want from that particular category. So how many green do we want? 2. We want 2 to be green. How many blue do we want? 2. There you go. And 3 will be yellow. 3 will be yellow. And that's it. Once again, I'm not going to evaluate this combination, but you put that into your calculator, you get the answer. Ta-da! And as you can see, there are more than 2 categories here. We've got 1, 2, 3 categories, but it's exactly the same. And if there were 4 categories, you'd put the 4th one over here. Up here would go the total of how many things are in that category, and over here would go how many you want from that category to appear in your selection. It's very formulaic. Okay, next question. I'm attempting to not go off the screen here. The results of random surveys show that 70% of students listen to music while studying for an assessment. Okay. You should really be thinking what this could be. A random sample of 5 students selected found the probability that more than 3 students listen to music while studying for an assessment. Okay, now when they give you percentages, it's always a clue that they are probably talking about a population. In other words, a group of people so large that when you select one at random, it does not affect the probabilities. So if I told you that 50% of all Americans are supporters of the Republican Party. Now, if I choose one American at random and put them aside, when I make my next choice of an American, what is the probability that they are a Republican? It's pretty much still 50% because there are so many Americans. So when your group is large, percentages are a kind of a hint that the selection process does not change the probabilities that are underlying the outcome, which means repetition is allowed. That's how you should think of it. Repetition is allowed. So what we've got here, repetition is allowed. How many outcomes? Only 2. They either do listen to music or they do not. So we have only 2 outcomes. Repetition is allowed. If you've studied, you'll know this is the binomial distribution. So we can go down and look for the binomial distribution, wherever it may be. There it is there. I grab it, copy it, we use it. Okay. And now we read the question. The random sample of 5 students is selected to find the probability that more than 3 students. Okay, more than 3. Well, now, this is always where you need to ask yourself whether you're going to use the 1 minus trick or not. They're asking you for the probability that more than 3, in other words, x larger than 3. Do they say more than or equal to? No, it's just more than. So there is no equality there. It's only greater than. And you must, if they had asked something like the probability of x being more than 1, well, that's the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. Those are all the probabilities you'd have to work out, because those are all the possible scenarios. In a random sample of 5 students, you could have 9 listening to music or 1 listening to music. But if you want more than 1 to listen to music, it means you want 2 to listen, or 3 to listen, or 4 to listen, or 5 to listen. That's 4 possibilities for you to consider. That's a lot. That is when you would rather use the 1 minus trick, and you would say, aha, this is actually equal to 1 minus the probability of x being less than, or equal to 1. In other words, just work out the probability of 1 and the probability of 0 and subtract that from 1, instead of working out the probability of 2 and 3 and 4 and 5. It's much faster. That's the 1 minus trick, which we have discussed a few times in the lectures that everybody attended. Now, in this case, we're not going to do that because it's greater than 3. So what possibilities are there? Well, that's the probability that x equals 4. There's no equality, so we do not have to do the probability that x equals 3. We only have to do the probability that x equals 4. Or, and this binomial is always mutually exclusive, so you can always add the probabilities. The probability that x equals 5. It's a random sample of 5 students, so how many could listen to music? Either 4 of them could listen, or 5 of them could listen. Any other number doesn't work. So you could sort of write it like that, and we use the formula now. We put the numbers in. What's this going to look like? I'll write the things out first. Just always go back and check what p normally represents the thing you want, and 1 minus p normally represents the thing you do not want. Often it's stated as success and failure, but we don't have to be so harsh here. Studying without music is not a failure. So we just ask ourselves, okay, the results of a random survey, what do we want? Find the probability that more than 3 students listen to music. So we want them to listen to music while studying for an assessment. What's that probability? 70% of students listen to music. Okay, so p, we could write that up here if you want, by the way. P is 0.7. Quick maths tells you that 1 minus p is 0.3. That's just for the next bracket. Okay, now, what are we going to do? Well, little x equals 4. I mean, you can just compare the formulas if you've forgotten what it means. Big X, here's a big X here, here's a big X here, here's a little x here, so 4 must be the little x. So there must be go 4 there. That's if you've forgotten how the formula works. If you haven't, well then you can go, oh well, I know what this means. N is the total that you're choosing, x is the outcome that you want. So how many are we choosing? We're choosing 5. P, as we already said, is 0.7. And how many do you want to be of that nature? You want 4, so it's to the power of 4. 1 minus p is 0.3, and how many do you want to not be of that nature? Well, it's the one left. It's n minus x, which is 5 minus 4, so that's 1. Plus this one here, same story, just fill in the gaps. It's 5 is the total. Clearly, little x is also 5. 0.7, how many do you want to listen to music? You want 5 to listen to music, so the 70% chance of listening to music is put to the power of 5. And how many do you want to not listen to music? 0.3. You may as well do this step. You want none, so that's the power of 0. Now, of course, this evaluates to 5 times 0.7 to the power of 4. My 4s are a bit ugly. Times 0.3 plus 5 combination 5 evaluates to 1. 0.3 to the power of 0 evaluates to 1. So this is just 0.7 to the power of 5. Equals, you ask your calculator. I'm just checking if things are still recording over here. Okay. You just ask your calculator and put that in. Once again, in the interest of time, I'm not going to evaluate this, but that's the answer. You put it in and you laugh with joy as you know you got everything right. Okay, we move on to the next one. By the way, we've covered those quite extensively in class, so not too much of a surprise there. The next few questions involve things that we perhaps have not covered in class. A player throws 3 darts, let x represent the number of darts that hit the bullseye. The probability distribution of x is shown on the table with some unknowns. Notice P and Q are unknown. Don't read anything into that yet. There's nothing on the formula sheet about P's and Q's that you need to know. But they're unknown quantities that we have defined using the expected value. And okay, by the way, for the students of 4 is high who might be watching this, hopefully that's all of you. Well, not hopefully, but probably that's all of you. At this point in the course, this was covered in the very last lecture where almost no one was in attendance, to speak truthfully now, and it was covered pretty quickly too. So this might be the part that seems completely foreign to you, so now you actually have to pay real attention. And if it seems totally new to you, well, it is. Given the expected value is a certain number, find the values of P and Q. Okay, this isn't actually that bad. Expected values, let's quickly discuss what this is. This is a probability mass function. It's not given as a function, it's given as values. But this would be f of 0, this would be f of 1, this would be f of 2. Each number underneath it is what I'm talking about. F of 3, so f of 0 is 0.5, f of 1 is 0.35, f of 2 is p, f of 3 is q. For every number in the domain, you can put that number into the function and a probability comes out at you. What's that called? When you put in a number in the domain into a function and it spits a probability out at you, that's called a probability function. If the numbers are continuous, it's a probability density function. If the numbers are discrete, it's a probability mass function. These numbers are discrete, so it's a probability mass function. So that's what this is. It's just given to you in a table instead of as a formula. And there are 2 formulas that you use to analyze things like this. Here they are here. There's the one there, which gives you the variance of a probability mass function. And here's the other one here, which gives the expected value of a probability mass function. And by the way, what is the variance, if you're wondering? What is var? Well, it's very easy. The variance is equal to the standard deviation, which you've all heard. It has many different symbols. Sometimes they call it S, sometimes they call it sigma. But the trick is it's the square. The variance is the standard deviation squared. So it's S squared or it's sigma squared. So once you work out the variance, if you're asked to work out the standard deviation, you better take the square root at the end because it's the square of that. That's what variance is. How about expected value? Well, this is just the mean. The expected value of a distribution is actually just the mean, x bar. If you're talking about a sample, also known as mu, if you're talking about a population. It's the average, or the mean. That's what the expected value. Okay, so we can grab some of these. They're asking us, given that the expected value of x is something, find p and q. So they are telling you, given that the expected value of x is something, find the values of p and q. Well, they're not giving it to you, but it's pretty obvious that you're going to have to use this expected value formula because they're giving you the expected value. So let's use it. There it is there. Now, what does this mean? Summation. It means add everything up. Very straightforward. X times p of x times x. So you just have to check what's x. It's this row here. What's p of x equaling x? It's this row here. So it's actually quite simple. All you're going to do is you're going to take the number in the x row and multiply it by the number in the p of x equaling x row. You're going to multiply them together and then you're going to add them all up. And that's it. Okay, so we do it. Very straightforward. Ooh, oopsie. So let's do it. It's equal to what? Well, we get started. The first value of x is 0. Okay, let's put it in, just for the sake. It's 0 times 0.5. That's x times p of x. Plus, the plus is because of the sigma. We're adding everybody up here. X, the next x is 1, multiplied by 0.35. Okay. This is a somewhat ambiguous question, but you'll see, I'll show you the ambiguity in a second. And we will resolve the ambiguity in a second. 30 minutes already, that's pretty interesting. Okay, plus 2 times some probability, p, we don't know, plus 3 times some probability, q. Okay, we could kind of work that. In this case, I probably have to do it. This times this is 0. This is 0.35 plus. So 1 times that is 0.35. 0.0 times 0.5 is 0. Nothing to say there. Plus 2p plus 3q. It's equal to 0.67. Okay, this is actually quite interesting. We'll see how this is resolved in a second. So, well, this is supposed to be an implication, not an equality. There's implication, there's implication. So I'm just going to use my calculator here quickly, which I do not think you can see, but it's 0.67. I'm just doing 0.67 minus 0.35. It's 0.32. So we get to the 2p plus 3q equals 0.32. Now, you have to use some how do we say this? You have to make a few assumptions here. Well, let's just talk about this. This is not the greatest question in the world, now that I analyze it, but it certainly captures everything we need to know. And the understanding is there, the formula is correct. The only problem here is you can't really solve for p and q without doing some further, without making a few further assumptions. Because as you can see, it tells you that the expected value of x is 0.67. They want you to find the values of p and q, and they don't really tell you much else about it. In other words, p and q can be anything. For example, let's make p equal to 1. Well, then you get the equation, sorry, let's make p equal to 0.1. Well, then you get the equation 0.2, which is 0.1 times 2, plus 3q equals 0.32. You perform a subtraction and you get that 3q equals 0.32 minus 0.2, which is 0.12, leaving you with q equals 0.04. And what I'm trying to show you is, at this point, it looks like any values of p and q might work. Well, not any values, but it looks like you can just make p something less than 1, and then q will follow suit to accommodate whatever you've done, just like what I've done here. So whatever you choose p to be, as long as p is less than 1, because p is a probability. This is already a hint to how you actually solve this problem. But because p is a probability, you should always keep in mind it has to be less than 1, it actually means something even more than that, which we'll do in a second. But initially you think it must be less than 1, not more than 1. So as long as you make p less than 1, so you make it 0.1, you can make it 0.5, you can make it, you have many options to make p. And as you see by this calculation, whatever you make p, as long as it's less than 1, you've got a legitimate value for probability. You've solved the rest of the equation, and q will become whatever it needs to be to accommodate your choice of p. So it doesn't seem to be unique. There doesn't seem to be a unique way to assign values to p and q, but then you think to yourself, wait a second, p has to be less than 1 because it's a probability. Q has to be less than 1 because it's a probability. Are those the only constraints on probabilities? Well, this is the aha moment. Here's where you go, oh, okay. Those are not the only constraints on probabilities. They do not only need to be less than 1, they also need to add up to 1. And that's the second piece of information. So all of this is just fanciful messing around. You can then go, wait a second, the sum of all the probabilities of a distribution must add up to 1. Remember, those are the two critical things of a probability. It must be less than 1, and the sum of all the probabilities must add up to 1. And also, they can't be negative. You do get negative probabilities, but that's crazy talk. So, okay, so we just put that constraint in. The constraint is that 0.5, which is the first probability, plus 0.35, which is the second probability, plus p, the third probability, plus q, the fourth probability, must add up to 1. Because it's the sum of all probabilities. And now we are happy, right? Because now we have a set of simultaneous equations, 2 unknowns, 2 equations. We're good to go. Let's simplify this first equation quickly. What does that tell you? It tells you that I'm just using the calculator app, which I do not think you can see at the moment on this recording. 1 minus 0.35 minus 0.5, so it's 0.15. So p plus q must be 0.15. And here you've got, excuse me, there's your first simultaneous equation, there's your second simultaneous equation. You combine them and you get the answer. It shouldn't take too long, so we can quickly do it. Let's check. What does this tell you? This tells you that shall I eliminate, using this equation, I will eliminate the variable q. Q is 0.15. You can also multiply and add and subtract, but this is a fast way of doing it. Q is 0.15 minus p. So you take that equation and stick it in here. What does that give you? That gives you that it's 2p plus 3, and now we eliminate the q, it's 0.15 minus p equals 0.32. Just by process of elimination, this gives you that, what are we going to get? We're going to get 2p minus 3p, so this is minus p plus 0.45 equals 0.32. I'm just going to solve this on my calculator quickly. 0.32 minus 0.45 is that. It's 2p minus 3p is minus p. Okay, so it turns out that p is equal to 0.13. You take this, you stick it back in there or there, either of these is fine, and you get out that therefore q must be 0.02. If you want to check the two simultaneous equations, you can. Let's check. P is 0.13, Q 0.02. So this would be 0.26 plus 0.0 plus 0.06 is 0.32, correct? Check the second one. If you add them together, you get 0.5. Okay, so there you go. There are your two answers. P is 0.13, Q is 0.12. The first of our simultaneous equations came from using the expected value formula. The second of our simultaneous equations came from using the fact that if you sum all the probabilities, they must add up to 1. Don't forget that. Very important. And there you go. That's the answer to that question. Let me get rid of all this nonsense. We continue now. Using the probabilities above and showing all working. So, let me not lose my answers. I believe that P was 0.13 and Q was 0.02. I don't want to forget those, so I'm just going to put them there. Yeah. Using the probabilities of and showing all working, find the standard deviation. Okay, it's another one of these formulas. I already told you it's this one, but remember at the end we have to take the square root because the variance is the square of the deviation. So we first figure out the variance. Now this one is a bit confusing, but once I explain it, hopefully you'll see. So I grab it and I put it here. Okay, now what does this mean? The variance of x is the expected value of x squared. Now, someone asked me a good question once upon a time. What is the expected value of x squared? It doesn't mean that you square the probability. It only means that you square the actual value of x. Let me say that again. Each x value has an assigned probability. You do not square the assigned probabilities when you are calculating this term. You only square the value of the variable. In other words, this thing, the 0, the 1, 2, the 3, that's the thing you square when it goes in here. You never square probabilities. The only time ever in mathematics or physics that you square probabilities is in quantum physics, which is not what we're doing. So just as a rule of thumb, don't square probabilities. It's a bad idea. So you square the numbers, but then you still use the formula for expected value, which was what, if you recall? You add everything up and times by its associated probability. So we're going to do the exact same thing we did the previous time, where you add up every value multiplied by its associated probability, except this time we're going to square everything. So let's do that. What's this one? It's 0 squared times its associated probability, which is 0.5. Do you notice I've taken the 0 and I've squared it because it's the expected value of x squared. But I have not squared the 0.5 because that is a probability. You don't do that. Plus 1 squared, because that's the 1, times 0.35. Plus 2 squared, because that's the actual number, times p, which we know is 0.13. Plus 3, which is the x squared. You always square the actual value of the variable. You never square the value of the probability. Times q, which is 0.02. Okay, that's all of this done. Minus this. What's this? This is the thing we actually just calculated, by the way. Well, not calculated. This is the thing we just used to calculate. This is much easier. This isn't the expected value of something where you have to square each entry. This is just the expected value, all squared, which means you take the expected value they give you and square it. So this one's always, or almost always, far easier to work out. It's actually just the expected value given to you or calculated previously, all squared. So, and bear in mind you have to subtract it. So what is that? Well, the question tells us, right? It's 0.67. So you minus 0.6. It's bad 6. 67 all squared. And there's your sum. This obviously comes out to be 0 plus 0.35 plus 4 times 2 squared is 4, so it's 4 times this number, which I believe is 0.52, plus 9, 3 squared is 9, so it's 9 times this number, which is 0.18, if I'm not crazy, minus, I'll just do this quickly, 0.67 times 0.67 is 0.4489. There it is there, and we work out what that is. It's 0.35 plus 0.52 plus 0.18 minus 0.4489. It's 0.6, and I think they asked for 2 decimal places, so but I'll fill out the whole thing. 0.6011. Of course, if they ask to 2 decimal places, it's 0.60. Now, what is that we just worked out? It's the variance. So we're not done. The variance is equal to the standard deviation squared. Therefore, the standard deviation sigma itself, that's a very ugly sigma, is the square root of this. So we find the square root. Which appears to be 0.3613. Now that's the square. Okay, we got to let me try that again. Miscalculation, 0.6 to the power of 0.5. Okay. So the square root of this seems to be 0.774. Which, if they ask you for 2 decimal places, as they are usually want to do, it rounds down to 0.77. By the way, I just took the square root of that number in order to get rid of the square rooting there. Don't forget that, please. Variance is the square of the standard deviation. So if you want the standard deviation, which is, as you see here, what they always ask for, you need to take the square root. Here's the full calculation in full. Okay. Let me get rid of all this now. We're making good progress here. Okay, question 3. Frequency. This is called a frequency table. It's literally telling you how many times does each variable pop up. So there's a certain variable. It can take certain values. This one can take the values 0, 1, 2, 3, 4. For example, if our variable was the outcome on a single rolled die, then the variable row would go 1, 2, 3, 4, 5, 6. Done. It can take the values 1 to 6. That is the possible outcome of a single rolled die. The frequency tells you how many times that outcome was observed. So, whatever this variable is, for simplicity it was not included, we saw it come out as 0 twice. We saw it come out once 3 times. We saw it come out as a 1 3 times. We saw it come out as a 2 5 times. As a 3 3 times, as a 4 twice. That's what these tables mean. And so this is a very standard thing. It's called a frequency table. And there's a very straightforward way of calculating the mean and standard deviation from a frequency table. I'm not going to do it now. I'll just put a link because there's 1,000 videos explaining how to do this. It's very straightforward and it's a very common task. Given a frequency table, you find the mean and the standard deviation. Just by the way, it essentially amounts to the same thing, because the frequency, if you think of it like this, a frequency can be turned into a probability. If you saw something twice, well then what was the probability of it? The probability would be 2 divided by the total number of things you saw. So you saw 1 2 zeros, you saw 3 1s, 5 2s, 3 3s and 2 4s. So how many things in total did you see? 2 plus 3 is 5, plus 5 is 10, plus 3 plus 2 is 15. You saw 15 things. So 2 over 15 would be the probability. We could put it down here. 2 over 15 would be the probability of x being equal to x. And so you just do that same calculation there and there and there, and then you've got a table that looks, guess what, exactly like this one. And so you do everything the same way. But I'll put a link to a video of how to work out expected values. I mean, now you're going to say 0 times 2 over 15 plus 1 times 3 over 15 plus 2 times 5 over 15 plus 3 times 3 over 15 plus 4 times 1 over 15. And that's the expected value. Standard deviation calculated similarly. Perhaps I'll try to find a video that even shows you how to quickly do it on your calculator, but I wouldn't recommend it because it's for 7 marks. So I recommend you show your working, which is working out the sample mean and standard deviation from a frequency table, and show your working for 7 marks. Okay, we go back. Continue. Okay, question 4. Same story, by the way. It's only 4 marks, but I believe many of you can do this from core maths. Once again, okay, you're given a table of data. Calculate the sample mean and standard deviation. I think from core you should be able to do this. It's a calculated thing. It's not something you should really try to do by hand. That's hard. There are formulas for it if you want to have a look. They don't even give you the formulas here, so no, never mind. There are formulas for it if you want to go through the rigmarole, but no one does that. You use your calculator, and you're allowed to use a calculator. It's only for 4 marks, which means put it in your calculator, get the answer. 7 marks means that just showing what your calculator gives you isn't going to be enough. But 4 marks, you can be confident that just showing what your calculator gives you is probably good enough. And so you put all of these numbers into your calculator and you ask it for the sample mean, which is, by the way, what is sample mean? It's x bar according to your calculator. And what's the standard deviation? Different calculators call it different things, but it is most usually called S of x bar. It's sometimes also called S of n minus 1. Those are the 2 different names given to it by different calculators, but it's the same thing. You put it in. Once again, I'll give a link to how to do this for anyone who doesn't know, but this is such a common task that it's not worth going over once again. Let me get rid of all these horrible features I added. Okay, question 5 and question 6. Formulas. Okay, consider the following probability density function. Immediately, you know, that means a continuous variable, not discrete. Discrete is mass. So this is discrete, which means you're going to use integrals instead of summations. I put this down here in the block to remind you. This doesn't get given to you. There's no formula sheet thing like this. You just have to remember. For probability mass functions, the variable is discrete, so you use a summation. It's 1, 2, 3, 4. For probability density functions, the variable is continuous. It's all real numbers. You can't just add them up. You have to use an integral. That's how that works. Okay, so this thing is discrete. We got a, excuse me, not discrete. I meant to say not discrete. It's a density function, so it's not discrete, it's continuous. So we're going to have to integrate. Calculate the value of k. So here's the crux of the matter. The value of k, whenever you are asked to calculate values for a probability density function or probability mass function, whenever you're asked to calculate values, it's called normalizing. This comes up a lot. They ask you to calculate the values of a variable for a probability density function or a probability mass function. It's called normalizing. And what you are doing is making this value k whatever it needs to be so that the probability density function is a valid density function. And recall what a valid density function needs to have. All of its values must be less than 1. That's how probabilities work. And if you add up all the values, you must get 1. Now for a continuous variable, you can't add up all the values, you have to integrate all the values. So if you're dealing with a probability mass function, the way it works is all the values must be less than 1 and all the values must add up to 1. That's a probability mass function. Probability density function, if you add up all the values, well, you can't for a probability density function. If you integrate all the values, it gives you 1. So we're going to do that. Calculate the value of k. Well, all we have to do is make sure that if you add up all the values, it'll give you, if you integrate all the values, excuse me, I keep saying add up because for me, adding up a continuous variable automatically means integration. So I just say add up. Do we have to check that all the values are less than 1? No, not if you've already ensured that they all add up to 1. Think about it like this. If you have a whole range of positive numbers and you integrate all of the positive numbers to get 1, they must all be less than 1. You can't have a range of numbers where some of them are more than 1 and you integrate them or add them and then suddenly you get 1. That will only work if some of them are negative. So you cannot add up a bunch of positive numbers to get 1 unless they're all less than 1. So you never have to check the less than 1 condition. That's the point I'm making here. Finding values of k or whatever variable in a probability density function or a probability mass function, you don't have to check that the thing is less than 1. You just have to check that it is positive, which I'm not going to check in this case, but you can easily see when x is between 4 and 6, f of x is strictly positive. So all you have to check is it positive and does it add up to 1? Okay, let's see. We want the integral of f of x dx to add up to 1. That's it. What else? As I just said, it must be strictly positive when x is between 4 and 6. Well, you can draw a picture if you want, you can do the critical values, you can draw a table, you can put in your calculator, you can just pray. Whatever you like to do, convince yourself that this thing will always be positive between 4 and 6. And then you perform this integration. Okay, I hope you know how to do this. It's the integration of k times x plus 1 times x minus 4. Bit of an ugly x there. Dx. Constants come out. So k comes to the front. Oh, and this should be equal to 1. I'll keep the implications here. Integration, I hope you all know how to do integration by the time the test comes. Or for anyone else in the world who might be watching this, learn integration. It's pretty cool and important. And sometimes fun. Okay, k, the integral of, now let's multiply this out because we don't want to do integration by parts. There's 2, that's a function of x, that's a function of x. We could do integration of by parts, it'll be way too painful. It's easier to just multiply this out. So what are we going to get? We're going to get x squared. I believe it's minus 3x minus 4 dx equals 1. Oh, and the limits of integration, you can put them in whenever you want, but the limits of integration are always the values of x where the thing actually has a value. In other words, what's the lower limit here? It's the lower limit here, so it's 4. The upper limit here is the upper limit where the function actually has a value, so that's 6. You can put these in wherever you want. You don't have to put them in at the start. So this is between 4 and 6. Okay, let's check. It's x squared minus 4x plus, that is minus 3. Okay, that all works. Now you perform integration. What do you get? You get k, and here you get some stuff which is going to be evaluated from 4 to 6, and you want that to be equal to 1. What is this stuff? It's x cubed. Remember your integration, please. It's x cubed over 3 minus 3 over 2x squared. Remember, you add 1 to the power and divide by the new power. So add 1, you get 3. You add 1, you get 2 minus 4x. And then you get this big equation with stuff in it. You get this is equal to k times something minus something, and that must be 1. What are the somethings? This is what you get when you put in 6. This is what you get when you put in 4. So this is going to be 6 cubed over 3 minus 3 over 2, 6 squared minus 4 times 6. I'm just putting in the limits. What's this one going to be? This is going to be 4 cubed over 3 minus 3 over 2 times 4 squared minus 4 times 4. And I hope you can see what is this going to turn out to be. I'm not going to do the calculation in the interest of time, but there's some gobbledygook here. All of this gets chomped up into a number. You can just see there's numbers everywhere. There are no more variables. All of this can just go into your calculator, and you end up with something like this: k times some number, which your calculator will give you. You know, it could be 52, who knows, some number, equals 1. And the last step for you to do is to just divide and say that k must therefore equal 1 over whatever number you got, right? So this chomped up number goes in here, and then you divide by it, and that's your answer. I think you understand these last two steps. Not going to go through the pain of working out these numbers, but the idea is, let's talk about the big ideas here. The big idea is, when you're looking for a variable in a probability density or probability mass function, they want you to normalize it, which means check if the summation adds up to 1, or check if the integral adds up to 1. This is a density function, so you check the integral. The integral of what? The function itself. What are the limits? It's the limits that they give you for where the function has a value, where it's not 0, in other words. You make it equal to 1. You perform the whole integration, take out the constants, do the integration, put in the limits of the integral on either end to get a definite integral, get a number. You got something times k, you divide by that number, and you are done. Okay. Lastly, or second lastly, shall I say, find the median value of this PDF. Okay, we're not going to go through with this one, but I just want to show you what they mean by that so that you know. What is the median value of a distribution? Very straightforward. It's the middle value. The median value of a distribution is the value in the middle. How do we use it here? Well, the middle value of a probability density function is quite simply the value which has 50% of the data on the right and 50% of the data on the left. In other words, the integral up to the median of a distribution will come out to be 1/2. The integral after the median of any distribution will also come out to be 1/2. So if you want to think of it, you can think of it like this. On the x-axis you have little x. On the y-axis you have the probability that x equals x. You've got some distribution, maybe it looks like the normal distribution, who knows. What's the median value? Tsa. More like tsa. The median value is the value in the middle, which means that 50% of the data lies on the left, 50% of the data lies on the right. And what does that tell you? It tells you that if you perform the integral here from 0 to the median value, you will get a half. The area will add up to a half, which is 50%. If you perform the integral from the median up to, well, wherever it goes, possibly positive infinity, who knows, you will also get a half. So you take your pick, whichever one. Normally this one's easier because there isn't an infinity floating around. That's what the median does. So you set up the equation. What are they going to do? It's the integral. Well, the setup for this question here is that you're trying to find m. By the way, m is what you're after. what is it called? It's called the median, it's called the median value. And how do you work it out? You just set up the integral and you look for which limit of integration gives you a value of a half. So you want the integral which goes from 0 to whatever the median value might be of the function itself. To give you a half. That's all you want. Oh, excuse me, maybe I can just tidy that up a bit. Okay, you want that to give you a half. And that's what you want. And I could probably leave you here, by the way. You could solve this. You're looking for m. You chug, you get m. Some tips I can give you is, first of all, you're not actually going to start at 0 because the function itself does not start at 0. It starts at 4. So you can immediately change this into the integral from 4 to the median value of f of x dx equals 0.5. So what do? It's pretty straightforward. You work out the integral of f of x, which we already worked out, by the way, previously. It was something like x cubed over 3 minus 3 over 2 x squared minus 4x. I think that's what it looked like. That was the integral of f of x. So this is equal to the integral of f of x dx. You may as well call it capital F because that's a symbol that is often used. Capital F often implies the integral of little f with respect to x. So this is it. This is the integral of f with respect f of x with respect to dx, often called b of x. So what are you actually going to work out? You're going to say, well, big F, which is the integral, evaluated at the median value because that's the upper limit, so you put it first, minus big F, which is the integral, evaluated the lower limit, which is 4. It's the lower limit, so you put it second after the minus, equals 0.5. And I think all of you can solve this one. Pretty straightforward. You take 4, you put it in there, see what you get. You minus it from 0.5 by move it to the right hand side of the equation. F of m will just be a polynomial in the variable m. Right, so you're going to get m cubed, blah, 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 and you solve for m. If you understand what I mean, maybe you don't even have to do it. You can chug through it if you want. The idea is quite simple though. You find the integral of the function, which we're going to call capital F, and you find the value where capital F of m, which is the median value, minus capital F of the lower limit, which is where it starts, equals a half. Of course, equivalently, you could also do this. Instead of using the integral from 4 to m, you could also use the integral from m to 6, because 6 is the upper limit, if I recall, yes. And so what you would end up with is f of 6 minus f of m equals 0.5, same thing. And you solve for m. You take your pick, okay. If you understand the concept, you don't have to chug through this final step, but the idea is you put 6 into capital F. Capital F is just the integral of the function. Hopefully you can find it. You put 6 in there. You put m in. You subtract them to get some polynomial in the variable m equal to 0.5. So you shuffle it around and you solve for m. Okay. And now we're on to the last questions. This is the probability mass function, which means the variable is discrete. Have a look. 1, 2, 3, 4. It's discrete. No in-between values. Only 4 values, in fact. That's pretty discrete. Calculate the value of k. It's the exact same thing, except now we do not do the integral, we do the summation. So now we want to check that the summation of f of x adds up to 1. Previously we checked whether the integral added up to 1, or we insisted that it did in order to find the value of k. Now we check whether the summation adds up. Okay, the summation over what? It's the summation over all of these values. In other words, you have to add up f of x for all of these values. Okay, so let's do it. When x equals 1, what do you get? You get k times 1 plus 1 is 2, so it's k times 2 squared. That's it. It's very straightforward. I'm just using the function itself, and I'm putting in the values 1 and 2 and 3 and 4, and I'm adding them all up. That's the summation. So plus k times what? You put in the value 2. 2 plus 1 is 3, so this is 3 squared. We get the idea. When k is 3, you're going to get k 4 squared. And when k is 4, 4 plus 1 is 5, so you're going to get k 5 squared. This must be equal to 1. You insist upon it and you check whatever it needs to be. So let's see. This is k 4 plus k 9 plus k 16 plus k 25 equaling to 1. Let's see what we get here. I'm using my calculator, which you cannot see. 4 plus 9 plus 16 plus 25 is 54. So k 54 equals 1, and here we go. The answer is that k must be equal to 1 over 54. Done. A lot easier because it did not involve any integration, but a lot more computation, but no integration. That's how you find the value of k. You insist that the summation must be 1, as opposed to insisting that the integral must be 1 when you're dealing with a PDF. Find the mean of this distribution. Okay, well, there are actually different ways to do this. What I recommend is just make a table. You will never be asked this for a PDF, okay? So these two questions, they will never ask you this for a PDF. If you're thinking, no, but didn't they just ask us that? No, they didn't. They asked you for the median. It's not the same thing. The median of a PDF is not the same thing as the mean of a PDF. So they will never ask you for the mean of a PDF just giving you the PDF. They'll have to tell you more. They'll never ask you for the standard deviation of a PDF just giving you the PDF. They'll never ask you that. It'll always be for PMFs. So there are a few ways to do this. You could try use your imagination and go, okay, well, the mean must be, I'm not sure what you might think, but the idea for these two questions is that you use these two formulas, because that's the mean and that's the standard deviation squared. Remember, whenever you have PMFs, just like we did in this question over here, I said to you earlier in this video, I mentioned that this is actually a PMF just written out as a table. So whenever you have a PMF, probability mass function, you will be using these two equations to calculate the mean and the standard deviation. So this is a PMF, it says so in the question. So you're going to be using these two equations to calculate the mean and the standard deviation. I recommend making a table. Okay, what would the table look like? Something like this. On top you have all the possible x values. So what are the possible x values? It looks like it's just 1, 2, 3, and 4. And for each one you write down the associated probability, because as you see here, it's the top row is all the values that x can be. The bottom row is the associated probability. Now, where do you get that associated probability from? You get it from the PMF. You just have to work it out by putting in x. Remember, little x is the value up here, 1, 2, 3, 4. That's little x. When you take this little x and put it into this equation here, you get out f of x, which is the probability mass function, which is the probability that x equals x. This is given to you by the probability mass function. That's what that is. That's what the probability mass function tells you. It's the probability of big X equaling little x. Okay, so you just work it out. When you put in 1 here, what do you get? Okay, I think we did all of these already. You get 2 squared, which is 4. Times k, of course. Don't forget the k. But we already know what k is. We worked out k previously, by the way. Worked out that k was equal to 1 over 54. This was 9. This was 16. This was 25. K. But we know the value of k. You can put it in later if you want. Not so bad. And here we have our table, and we know k is not an unknown. There's the number there, so we can put it in if we want, but whatever the case may be, you have a table, and you just proceed as normal. You find the mean. So the mean is this formula here, once again, which just tells you take x, multiply it by its associated probability, and add them all up. So let's go. It's going to be 1 times k4 plus 2 times k9 plus 3 times k16 plus 4 times k25, and that's it. I'm not going to do this, but you work it out. Well, I guess we can. This is 100k plus 48k is 148 plus 18, 156. It's 160, 160k, something like that. So k is over that, so that's equal to 1. Well, let me just actually do this quickly. It's 4 plus 18 plus 48 plus 100. 170, excuse me, this is not 160, it's 170, so this is equal to 170k. You just add it all up. K is 1 over 54, so this is equal to 170 over 154, and that's the answer. That is the mean of this distribution, because it's the expected value and they mean the same thing. The expected value of a PMF or any given distribution is the mean of that distribution. So we'll divide this by 54. 3.14. Oh, it's basically pi. Very unintentional. 3.1481. If you care for more than just 2 decimal places, you can put in 81, but they'll only normally ask for 2, in which case it's 3.15. It's the mean. Now have a look. Does it seem like a reasonable mean of 1, 2, 3, 4 when the increasing probability of it occurring? 3.15. It does seem pretty reasonable. If you have these values 1, 2, 3, 4, and each one has an increasing probability of occurring, so 4 is actually the most likely to occur, what could the mean be? Oh, a little bit bigger than 3. Seems to make sense. Okay, standard deviation, same thing. Use this formula here, but then take the square root. Don't forget. This formula here tells you, first of all, you got to square everything. So first of all, you have to square everything and multiply it by its associated probability. That's the expected value. Expected value just means take the number, multiply by its associated probability. But here we're taking the number squared and multiplying by its associated probability, and then you minus the expected value, which we already worked out, by the way. Let's just remember that this is the expected value of x. And all squared. Okay, so what are we going to do now? We square all the numbers. Let's square them. What do we get? We get 1. We get 4. We get 9. And we get 16. and you multiply by its associated probability. Now the associated probability is not squared, so you continue to use these numbers, please. You do not square probabilities. So you add them all up. What do you get? It's 1 times k4 once again, plus it's no longer 2 times k9, it's now 4 times k9, because 4 is 2 squared, plus 9 times its associated probability, which is k16, plus 16 times its associated probability, which is k25. And okay, we may as well add this up. What does this give you? This gives you k4 plus 36k. Okay, for some reason I swapped my orders there, I don't know why. This is 144k, and lastly 16 times 25 is 400k. Let's add them all up. What do we get? 4 plus 36 plus 144 plus 400. I get 584k. Which is equal to 584 over, we know the value of k is 1 over 54, so it's over 54. So let's work that out. I get 10.8148. And that's it. But remember, that's the variance, which is equal to sigma squared. They asked for the standard deviation of this distribution, which is sigma, so we've got to take the square root of this number. Therefore, sigma, which is the square root of this number, is 3.2885. And once again, feel free to try use 2 decimals. This will turn into a 9 if you do round up. But that's the principle. Once again, we use these 2 formulas, and you can always use these 2 formulas when you have a PMF, in particular a table. And so I like to usually turn PMFs into tables so that you can quickly use these 2 formulas, which are designed to be used with tables. Okay, we're almost done. Last question. I've got a lot of untidy things going on here, but we don't have to worry too much about that. Find the probability of something. This one's easy. You just add up all the relevant probabilities. So the probability of x being greater than 2. Well, how can x be greater than 2? Let's check. X must be greater than 2. It can be 3, or it can be 4, and that's it. Can't be 1, because that's not included in the probability of x being greater than 2. It can't be 2, because that's not included in the probability of x being greater than 2. So this is it. It's equal to the probability of x being equal to 3 plus, and these distributions are always worked out to be completely mutually exclusive. They do not have overlapping outcomes. So it's plus the probability of x equals 4. And how do you get these probabilities? It's so easy. You just put the numbers into the equation. So this would be equal to what? This is where little x is 3. This is where little x is 4. You put in the numbers. So this is going to be k times 3 plus 1 squared. That is that probability there. So it's very easy. You just take the number that you're looking for, which is a 3 in this case, and you put it into the actual formula of the probability mass function. That's what it's designed to do. It's there to tell you the probability of x being equal to that value. Okay, plus, again, k. Now instead of x being equal to 3, x will now be equal to 4 squared. Please bear in mind, I'm using this formula here. There it is there, and there it is there. I've just put in the values of 3 and 4 because of this 3 and this 4. Okay, what's this equal to? This is equal to 16k, I believe. Let me double check that. 3, when x is 3, 3 plus 1 over here, yeah, correct, plus 25k, which is equal to 41k, which is equal to 41, and we know the value of k is 1 over 54, so it's equal to that. And this could even be your final answer, but let's convert to decimals. 41 divided by 54 is 0.7592. For those who like 2 decimal places, 0.76. That's it. That is your answer for the probability of x being greater than 2. All I did is I added up the value of the function for all the values of x greater than 2. And that's it. This was a lot of worked examples, many worked examples, but hopefully it helps, and let's see if anyone has any questions. So, thanks.